All right, so we are in our way well into unit 2. In fact, the end of this week is our test, right? I set that to actually be due Sunday at 5 again, rather than Friday at 5. So it's due Sunday at 5. It'll cover all the sections of chapter 3 up to 3.7. 3.9 obviously is not covered in that. And then 4.1 through 4.7 as well. So today we'll finish up what we can in terms of finishing log stuff, log properties, and then we'll go into solving exponential equations with logarithms. Next class period, we might be finishing up section 4.7, and then if we do we'll finish that up, and then we'll have some time at the end if you guys have any questions or anything like that. Okay, so that will be next class. All right. So last class period, we did a lot of work with logarithms. And we saw some of these log properties. One of them was our basic log base b scenario. If I have log base b of b to a power, then I just get that power back. That includes the power of 1 and the power of 0. We saw how log base b undoes b to the x, and how b to the power log base b undoes the log base b. So we get that nice property. And then we saw our product rule for logarithms, which said log base b of n times n is equal to log base b of m plus log base b of n. We saw our quotient rule. This was all from last time. Log base b of m divided by n is log base b of m divided minus log base b of n. And then we saw this power rule for logarithms, that if I take log base b to m to a power, I get that power times log base b of n. We also saw the change of base rule for calculating log base, any base of a number as well. Now, we're going to take a few moments just to do some rewriting with these rules. So we're going to take our product rule, our quotient rule, and our power rule, and we'll do some rewriting with this. So example 3 says take log base b of 82 plus log base b of 12 and rewrite it into a single log. And then log base b of 240 minus log base b of 15, rewrite that into a single log. And then we'll do the same thing if we have variables instead of actual numbers. So I'll do that as well. Log base b of 9x to the 5th plus log base b of 5x, and then subtract log base b of 9x to the 5th minus log base b of 5x. So we have this scenario. Or I should say these four scenarios. This first one, since we're adding the two logs, if I want to create a single log, I need to multiply what's on the inside. So I need to take the 82 times the 12 on the inside. That's what my product rule tells me I can do. 82 times 12. And that's going to be log base B of 984. $82 times 12 is 984. And that's it. That's the whole thing. This one is the right-hand side of the quotient rule, which says that if I take log base B of 240 divided by 15, then I get this, right? Quotient rule, log base B of 240 minus log base B of 15. Tells me I can do that. 240 divided by 15. Nice number 16 is what I get. So log base B of 16 is the correct answer. By the way, you can always check that by plugging in different values for B and seeing that that works. Okay. So I take natural log of both of this. And then natural log of that, take log base 10 of this. That doesn't always work, but if there's a few different logs with different bases, then you can check to see that that actually is true with various bases. Over here, I have variables inside. And so what I would do is I would exactly the same way. We'd take 9x to the 5th and then multiply that times 5x when we're adding the two logs. That's going to be log base B of 45 times x to the 6th power. And that's it. That's the whole thing. When I subtract, then we're doing quotient rule, log base B. This would be 9x to the 5th divided by 5x. So that's log base B. This would be x to the 5th over x gives me x to the 4th, 9/5. We can just leave that as 9 over 5. If you wanted to do a decimal version, you could write 1.8, 9 over 5, but that's it. So 9 over 5 times x to the 4th, 9/5 x to the 4th inside that argument. Now, the reason that this is nice is kind of shown here. If I have some equation that involves log base B of 9x to the 5th plus log base B of 5x, and that's set equal to a number, let's say, it's a lot easier to deal with this equal to the number rather than this form equal to the number. Does that make sense? So that's a really nice tool to have. These identities are really nice tools to have when we go ahead and solve equations with logarithms in them. Okay. So being able to combine two logarithms into one, very nice tool to have. Now, the product rule and the quotient rule are not the only two rules we just saw. We can also utilize the power rule in reverse. Here we have 4 times log base b of 5. We want to rewrite that as log of some number, log base b of some number. And then we have 3 times log base b of 4x to the 5th. And again, we want to rewrite that as a single logarithm. Okay. Let's do that one before I move on to the next. So this is applying the power rule in reverse. We're going to say, well, I know based on the power rule that if I have 5 to the 4th inside the argument of logarithm, I can bring the 4 out front. So if I have a 4 out front, I can rewrite this as 5 to the 4th. And then you just type that on our calculator, on your calculator, 5 to the 4th power, and that's 625. So that is log base b of 625. Now, be careful when you do that with an expression like 4x to the 5th. When we do log base b, we'd have to take 4x to the 5th and raise the whole thing to the 3rd power. Okay. So the 4 needs to get raised to a 3rd power. The x to the 5th would be raised to a 3rd power as well. When you do that, 4 raised to the 3rd power is 64. X to the 5th raised to the 3rd power is 15. So we get 64 times x to the 15th as the final argument inside that log. Again, these are nice tools to be able, both these and those are nice tools to have to be able to go back and forth when we're solving exponential equations and logarithmic equations. And that's what we're building up to, being able to solve those types of equations. Now, the other type of problem that you may see is a problem like this, where we may know the log of x. Let's say we know log base b of some x is 4. And I also know that log base b of y is equal to 10. And we want to calculate log base b of x times y. And we want to calculate log base b of x to the 5th. And we can do the same thing with more complicated logarithms, like log base b of x to the 3rd divided by y squared, or log base b of x to the 3rd times b to the 7th. I'll write those things over here. So if I know log base b of x is equal to 4 and log base b of y is equal to 10, then I'll be able to calculate log base b of x times y using the product rule. Product rule says if I have x times y inside the argument, then I can take log base b of x and add it to log base b of y. When I do that, this is just 4 plus 10, which is 14. So based on the power rule, I know that log base b of x times y is going to be 14. I want you to try to use like the power rule. We used to use the product rule. Use the power rule with the quotient rule here. Use the power rule here. Use whatever rules, product rule and power rules that we need to here. Try to do these other three on your own in the same fashion that I just did that first one. All right, so let me go through this. So here's the deal. On these, I don't know what x is, I don't know what y is, and I don't know what b is. But I know what log base b of x is, and I know what log base b of y is. So I need to break everything down into log base b of x, multiplied, added, whatever, with log base b of y. Multiplied, added, subtracted. So here, I don't have log base b of x. I have log base b of x to the fifth. But what I can do is I can rewrite that using the power rule as bring the exponent out front, 5 times log base b of x. Now, this entire log base b of x is just the number 4. I don't know what b is, I don't know what x is. So this is just 5 multiplied times 4. This whole logarithm gets replaced with a 4. And that's obviously 20 when I multiply 5 times 4. So even though I don't know what x is, I don't know what b is, I can compute that log base b of x to the fifth is 20 by using the log rules. In a similar way, I can do the same thing here. I can take and rewrite this as log base b of x to the third minus log base b of y squared. That's the quotient rule. So if I'm dividing two things, I can take log of the first thing minus log of the second thing, right? Log of my numerator minus log of my denominator. And then each of these is just like this. I take the exponent out front. This is 3 times log base b of x minus 2 times log base b of y. Now this entire log base b of x gets replaced with the 4. This entire log base b of y gets replaced with a 10. This is going to be 12 minus 20. So that's a negative 8 when it's all said and done. Again, this is, I don't know what b is, I don't know what x is, I don't know what y is, but I know what log base b of x is, I know what log base b of y is. So I can rewrite and manipulate and find an expression for that. Okay. Now on this last one, it's very similar. We're going to take, since this is the multiplying inside, we're going to take the product rule, log base b of x to the third, plus log base b of b to the 7th power. On this first one, this first part, it's going to be 3 times log base b of x. What's this number going to be? Sorry, the second number. 7. Yeah, that's the rule of logarithms. If we have base b and we're taking the argument of b raised to a power, that just gives me the power back, right? So this is just 7. Another way you could have thought of that, you could have brought the 7 out front, and log base b of b to the first power is just 1. So another way you can see that. But that's just 7. This base and this base match up, so you just get the power back. Okay. So that's 3 times 4, which is 12, plus 7, which becomes 19. Any questions about those? Again, rewriting using the rules that we have to come up with this. These problems can't be done any other way because it doesn't tell us what the x and the b and the y are. Okay. You'd have to go in, I should say, it's not something you can plug into your calculator and get. Okay, you'd have to go in a really roundabout way to come up with something you can do with your calculator. So these types of problems really rely on the logarithm rules. Now, last class period, we also saw the change of base rule. And we also saw that on our calculators on TI-84s, you can simply plug in log base b of whatever number, right? So just as a reminder of that, I'll do just one example. I know we did this last time, but as long as we have a base that is positive and not equal to 1, we can use our calculator to do things. So if I wanted to, I could say, well, let's take log base 2 of 47. What we're asking is 2 raised to what power gives me 47, right? And what I can do well, I can do this a couple of different ways. One is I could use the change of base rule that would say, let's take natural log of 47 divided by natural log of 2, or log base 10 of 47 divided by log base 10 of 2. So I can take natural log of 47 divided by natural log of 2 on my calculator. That would give me about 5.55. So 2 raised to that power would give me 47. 2 raised to the answer should give me 47. Okay. I could have also done that with log base 10 as well and gotten the same thing as long as I take log base 10 on top and bottom. 47 over 2. So that's the change of base rule. And then we also saw last time, if you go into your math menu, scroll all the way either up or down. I like doing up because there's only 2 up arrows, up or down arrows. So go up to log base. In my calculator, I have nice math print. And so I can just type in log base 2 of 47. And sure enough, you get the same answer regardless, right? So if you want to do log of any other base other than natural log or base 10, we have the natural log here. Oops. The natural log down here and the log base 10 right here. Next to the 7 and the 4, essentially. any other base you can do as well, other than base 10 and base 8. Oh, hit the wrong button. There we go. Good. So whichever you like, you can do. If you like the change of base rule, if you like the just typing in our calculator in the math menu, log base, whatever, you can do that as well. Okay. So now that we have all these tools to simplify, the reason why we are looking at these tools primarily is to be able to solve equations, both exponential and logarithmic equations. So we want to be able to solve exponential equations, we want to be able to solve logarithmic equations, and then solve applications involving those things. All right. And that's what the next two sections are. Solving exponential logarithmic equations and then using applications of those. Okay. Now we've seen exponential functions before. Just so that we're clear, an exponential equation is an equation involving at least one variable in the exponent. Okay. So you can imagine taking 7, raising it to the power x, and setting it equal to 49, and trying to solve that equation. That was pretty straightforward because we know that 7 squared is actually equal to 49, right? On the other hand, something like 1,200 is equal to 300 times the quantity 1 plus 0.05 over 12 raised to the 12t power. That was less intuitive. And so we're going to need a little bit more tools on that second equation, solving that one, than we would on the first equation. That makes sense? So we're going to be solving these exponential equations, figuring out what the variable has to be. In the same manner, when we talk about a logarithmic equation, we don't need any equation that involves log. Like if I have log base 2 of 47 is equal to x, that's not a logarithmic equation because I can just calculate log base 2 of 47. That's what we just saw, 5.55. What a logarithmic equation is in this class is it's an equation involving at least one variable in the argument of log. So on the inside of those parentheses, log of something. So something like log base 2 of 3x plus 1 is set equal to 6 would be a logarithmic equation. And we'll solve these as well. Now, this is a property that we used earlier in this class in a previous section, but I want to point it out and all of its relatives right now. So we actually used this property earlier, or at least we argued for the property. And this property says if I take a base raised to the x power and set it equal to that same base raised to the y power, that's going to happen if and only if x and y are the same. Okay. As long as my base is greater than 0, not 1. So positive base, not 1, our standard assumptions on any basis. Again, we used that earlier when solving equations. We'll use that again. We'll also use some other very similar arguments. One of them is saying, well, if I have a base raised to the x power, and that's set equal to a base raised to the x power, then that's going to cause my bases to be equal as long as that's true for all x's, is what I'm saying. Okay. Or even if we have a specific x, as long as x is not the 0 power. Does that make sense? We're assuming everything's positive, not equal to 1. So similar to our first thing, if I have our first one was if we had base raised to the x is equal to base raised to the y. If I have log base b of x is equal to log base b of y, then x and y have to be the same as well. As long as they both exist, as long as both of those things exist. Okay. Again, we're assuming things exist here. And then in a similar way, if I have log base a of x, is that set equal to log base b of x? Then a has to be equal to b, as long as we have nice values of x for that to work. Again, we're assuming all kinds of nice assumptions about a, b, x, and y. That we can plug them in and they exist and all that stuff. So same bases, same exponents, same arguments, force equality. And anytime I have that, I can take advantage of it. Let's take a look at these two examples. We have 5 raised to the 2x minus 1 is set equal to 5 raised to the 5x plus 11. And then 8 raised to the x power is equal to 2 raised to the power of x plus 14. This one is pretty straightforward. We have the same base. So this means that the exponents have to be equal. And then I can just solve for x. Now we've went from an exponential equation into a linear equation. And that linear equation obviously is easy to solve for x. Okay. So we would just subtract 2x from both sides. Subtract 11 from both sides. And that would give me negative 12 is equal to 3x. Dividing both sides by 3 gives me an x value of negative 4. So this means that in order for this equation, this exponential equation to be true, x has to be negative 4. And you could plug that in as well. take 2 times -4 minus 1, you get a -9. So the left-hand side is 5 raised to the -9 power. And if you plug that in here, 5 times -4 plus 11 is also -9. So that's 5 raised to the -9 power. So both sides are 5 raised to the -9 power. On this one, while I don't have the same base right now, I can manipulate 8 by rewriting it as 2 raised to the 3rd power. So 8 is 2 raised to the 3rd power, and that means 2 raised to the 3x power is the left-hand side, and 2 raised to the power of x plus 14 is the right-hand side. Now I do have the same base, so I can just set the exponents equal. And we would get 3x is equal to x plus 14. And now we're solving a linear equation. When you do that, you'll end up getting an x value of 7. And if you want to check that, you could plug that back in. This is going to be 8 raised to the 7th power. This is going to be 2 raised to the essentially 21st power. And you can check that those things are the same. They are. But. So if I don't have same bases, sometimes I can manipulate it so that we do have the same bases. Rewrite, manipulate, use the rules of exponents so that I do have the same bases. That can be applied with those other rules as well. This type of solving technique can be applied to the other rules as well. Here we have 9x minus 1 in parentheses raised to the 7th power set equal to 8x plus 8 raised to the 7th power. The 7th power is such. Well, let me write the other one down too before I get over my skis. So the other one is log base 3 of 4x minus 1 set equal to log base 3 of 2x plus 9. So on this one, the 7th power is such that I can set the bases equal. Okay, that power is really nice. If I had raised to the power of 0, then I'd be in trouble. Okay, because anything raised to the power of 0 would be 1. That doesn't make any sense. But raised to the 7th power, that's a nice power. Therefore, I can set the two bases equal to each other, and then I can solve. Again, that's solving a linear equation. I would end up getting x is equal to 9 when I do my solving, when I subtract 8x from both sides and then add 1 to both sides. I get x is equal to 9. Same principle over here we had with exponential equations. We have logarithms set equal. They have the same base. Therefore, the arguments have to be, okay, the arguments inside the logarithms have to be equal. So 4x minus 1 has to be equal to 2x plus 9 in this case. And then we do the same thing. We're solving a linear equation here. That gives me 2x is equal to 10. Dividing both sides by 2 gives me an x of 5. Again, if you want to plug that in and check that it works, you can check that it works. Any questions about these same bases, same exponents, same log with base type questions? These ones are pretty straightforward. They don't take a lot of technique. I mean, sometimes you have to manipulate 8 into like a 2 to the third, but that's about as difficult as anything that happens in these scenarios. Okay. But most exponential equations and logarithmic equations aren't easily written into logs with same bases. So in general, if I can't do that, if I can't rewrite an exponential equation to look like 7 raised to a power is equal to 7 raised to a power, then what I would do is I would isolate the exponential part, the exponential term, and then I would apply a logarithm to both sides. By applying a logarithm to both sides, we've seen the rule that says if I take log of b to the 7th power, I get 7. Well, log base b of b to the x power would just give me x. So that takes the variable that was in the exponent and it puts it down in front. You get that? Okay, it's this rule. Log base b of b to the x is equal to x. So if I apply log base b to b to the x, I can just get an x. And by the way, even if we have weird bases, like if I'm applying log base b to m to the x, I can still use that power rule and bring the x out front. And then I'm dealing with maybe a linear equation now, hopefully. Okay, so it's these two rules that we're going to be using, the essentially power rules for logarithms when we do that. So let's take a look at some examples. Here I'll start out with base e. Let's say I have 4 times e raised to the x power set equal to 250. And then I have e raised to the power of 3x minus 4, then adding 10 and setting that equal to 1,250. So the first thing I want to do in these cases is isolate the e to a power. And because that power has an exponent, right? Variable, has a variable in the exponent, excuse me. So I'm going to isolate that. In order to do that on this first one, I'm going to divide both sides by 4. Okay. 250 divided by 4 is 62.5. So I'm going to get e raised to the x power is 62.5. Now, people kind of mentally process this in different ways, right? What I like to do most of the time is just apply natural log to both sides. Some people would say, well, let's rewrite this exponential equation into a logarithmic equation. Okay. I just like to say, let's apply natural log to both sides. So I'm going to apply natural log to both sides. And I'm applying the natural log because natural log is log base e. Okay. So when I apply natural log to e to the x, since we have the same base, the natural log and the e will cancel each other out, and we'll just be left with an x on the left-hand side. That's the rule I was just talking about a moment ago. Okay. Log base e of e to the x just gives me x. And then on the right-hand side, I get natural log of 62.5. Now, this is actually the final answer, and this is the final exact value answer. You can obviously get an approximate answer, which is what Moodle's going to ask you for, by just plugging this number into your calculator. Right? So taking natural log of 62.5 gives an approximate answer of 4.14. That's rounding to 2 decimal places. Does that make sense? So this is the exact answer, natural log of 62.5. This is the rounded answer, 4.14. Again, sometimes people I like thinking of applying natural log to both sides. Sometimes people will take this and rewrite it as a logarithmic equation, which is actually just this, if that makes sense. It's saying x is equal to natural log of this. These two are the same equations. One is written in exponential form, the other is written in logarithm form. But again, it's a little bit easier for me to think through just apply natural log on both sides. That gets rid of that exponent, brings it out front, down. So whichever way you like, you can do that. I'm just going to apply logs to both sides most of the time. All right, let's do this other one. So the first thing we do is we subtract 10 from both sides to isolate the e to a power. Now I've isolated e to the 3x minus 4 power and got that equal to 1,240. I have e to a power. Therefore, I can apply natural log to both sides. Now, natural log of e to any power is just equal to that power itself, right? So it doesn't matter that our power is 3x minus 4. natural log of e to the power 3x minus 4 is going to be just 3x minus 4. And the right-hand side is natural log of 1,240. So regardless of what the power is, the natural log and the e essentially cancel each other out. They're inverse functions of each other on the appropriate domains. And that's what we end up with. And so this I can solve for x. Remember, this thing is just a real number. Okay? This is just some irrational number. So if I want to solve for x, I would add 4 to both sides. I would end up with 3x is equal to this number, natural log of 1,240, and then plus 4. And then I divide both sides by 3. So the exact answer is natural log 1,240 plus 4, all divided by 3. Obviously, like again, in Moodle, you're just gonna use your calculator, get an approximate answer, get a rounded version of that. So, natural log of 1240 in my parentheses, plus 4 on the outside of the argument, and then divide by 3. I get about 3.71. So you guys all got it. I did that in 2 steps. Make sure you add the 4 to that natural log before you divide by 3. But should get about 3.71 roughly. Is that all right? Not too crazy. Not too crazy. Good. Then I want you to try these 2 on your own. One of them is base e, the other is base 10. But remember, we have a log base 10 button on our calculator, so that's perfectly fine too. So we have one that's log base e, just like we had the first 2 examples. And then we have one that's base 10, 10 raised to a power. So try these 2 on your own.
Log 10 is just like log normally, right?
Yes, log on your calculator. Yep.
Thank you.
Yep. All right, so let's do these. First thing I want to do is isolate the exponential part with the variable. So dividing both sides by 500 on this first equation would give me e to the 0.07x power is equal to 7. Okay. And then, again, I like to apply natural log to both sides. Once you've done that enough, a lot of times people would skip this step, skip writing this step, and just write, oh, that's 0.07x is equal to natural log of 7. So I like putting all the steps in when I'm taking notes, but if you're hard pressed for time, skip that step. Then to solve for x, all I have to do is divide both sides by 0.07. Be careful when you do that. It's natural log of 7 here. Argument to 7 and dividing by 0.07. So don't put the divide by 0.07 inside the argument, in other words. We'll get an exact value of natural log of 7, all divided by 0.07. And that's about 27.80. Now, I want to point out something before I move on. Remember our equation for compounding interest continually? A equals P times E raised to the RT power. Well, we could have thought of this as the output, saying that if we put in $500 and compounded interest at 7% continually, how long would it have taken until that $500 turns into $3,500? And the answer to that would have been about 27.8 years. Okay, does that make sense? So that's where this is going. We're going to essentially be solving this with some application equations that we've seen before. All right, let's take a look at this second problem on the board. We would want to add 400 to both sides. That would give me 10 raised to the 2x plus 1 power is equal to 4,900. Since I have base 10 here, what I would do is I would use log base 10 on both sides instead of using natural log on both sides. And log base 10, I think I mentioned earlier, it's just log on your calculator. So log base 10 is log on your calculator. On the left-hand side, we get 2x plus 1. On the right-hand side, we have log base 10 of 4,900. And then we'd add 1 to both sides, divide both sides by 2.
What did we subtract from the whole
Oh, sorry, yeah, subtract. I'm looking. Subtract 1 from both sides. I subtracted, right? Yeah, I subtracted. And then divide by 2, excuse me. I ended up with about 1.35-ish. Okay, as my X value. And that's it. By the way, if you ever want to check that, you can plug it in and see what happens. Okay, plug it into the original equation, see what happens. Any questions about that? If you have log base E, log base 10, applications. Now, if we have any other base that's not one of the 2 buttons on our calculator, then I have a couple of different options of how to solve something like 2 raised to the x equals 30, or 1,500 times 1.04 raised to the x power is equal to 8,500. So there's essentially 2 options, and I'll go over both of them. All right. So we have another base other than E, other than 10. This is what we can do. Okay. So I'll do option 1. First, and then option 2 second. It doesn't matter which one you do. Or if you know both of them, I want you to be able to do one very efficiently. And if you don't do the other one at all, that's perfectly okay. Make sense? All right. So with the 2 raised to the x power equal to 30, that equation, we already have our exponential part isolated. So I don't have to add, subtract, multiply, divide before I start my thing. One option that we could do is take log base 2 of both sides. Since our base on my exponential piece is 2, I could just take a log base 2. Okay. On the left-hand side, that would become x. And on the right-hand side, we'd have log base 2 of 30. Now, we know how to calculate this in 2 different ways. We saw that both earlier today and also last time. You can either do a change of base, where we do natural log of 30 divided by natural log of 2, or log base 10 of 30 divided by log base 10 of 2, or you can just plug that in through the math menu feature on your calculator. Does that make sense? So whichever way you do that is fine. By change of base or just plugging it in. Erase this. Doesn't matter. We end up with about 4.91. So we're saying 2 raised to that power is 30. About 4.91 power is 30. Again, you could have also plugged it in direct, not used the change of base. So that's option 1, is just to use the base that we're given. Option 2 is to use like natural log or some other base. You could have also used base 10 if I would want to, and apply natural log to both sides. I tend to use natural log just because that's my go-to, but other people might use log base 10 because that's their go-to on the calculator. But on this, what we would do is we would use the power rule of logarithms, and we'd say natural log of something raised to the x power is the same thing as if I pull that x power out front, and then I have natural log of 2. We okay with that rule? Pull the x power out front, natural log of 2. And then I would divide both sides by a natural log of 2. This is just some number. So we would end up with x is equal to natural log of 30 divided by natural log of 2. Which is the exact same thing I had over here with change of base. Now you can see why the change of base rule works. That makes sense. This is exactly why the change of base rule works. So in this case, you also get 4.91. Roughly. So whether you would, doesn't matter to me, whether you would take log base 2 of both sides or natural log of both sides, both are going to lead to the same answer. Both are going to give you the same thing in the end. Okay. Some people like applying natural log just because that's an easy button to find on your calculator, easier than log base 2 anyways. Other people, they get used to using log base 2 on their calculator, so they just use log base 2. Or log base whatever the base is. Okay. I want you to try this one on your own, using either log base 1.04 eventually, or you can do natural log of both sides, pull the x out, either way. So try this one on your own. That's a 1.04 raised to the x power. Here, then we have times 1500 is equal to 8,500. Other than that, yeah, right. Oh, can't get rid of the coefficient. Yeah. All right, so let me go through this. Regardless of which option you use, we still have to get rid of that coefficient out front before we apply our logarithm. So we would divide both sides by 1500. And when I take 8,500, when I take 8,500 and divide it by 1500, I get 5.6 repeating, or 5 2/3. I'm going to just write that as 17/3. If that's all right. It's easier to write it that way. But you can leave it as 5.6 repeating if you want to. Just make sure you don't like put 5.7 into your calculator, because that would throw your calculations off. Does that make sense? But you can use 5.6 repeating. Now I have, again, the two options. Doesn't matter which one you utilize. I can take log base 1.04 of both sides. Or I can take natural log of both sides. Very good. So either way, perfectly all right. If I take log of base 1.04, I'll just get x on the left equaling log base 1.04 of 17/3. And I just typed that in my calculator. Here, I would get x times the natural log of 1.04 is equal to the natural log of 17/3. Which means when I divide both sides by a natural log of 1.04, I end up with natural log of 17/3 divided by natural log of 1.04. That's also the change of base rule on this, right? So in either case, I get about 44.23. They have a preference one way or the other. No. Right hand side. This one, using like a log base 2 sometimes looks nicer when our base is 2. When our base gets really complicated, it might not look as nice. And so sometimes people prefer the natural log method when the base looks complicated. Or when the base looks nice and easy, like just 2, then they'll use that. So they'll use a mixture of both sometimes. But that's what it is. Let's do one more of this type of, what was that? I had that up. Scenario. I'll go ahead and do this. Instance. So this is 1200, 1200 is equal to 1 plus 0.04 over 12, all raised to the 12x power, set equal to 30,000. You could imagine a problem where this came up. This could come up in a problem where they say you put in 1,200 and it compounds at a rate of 4% interest monthly. How long does it take to reach 30,000? All right, so let's go through this. The first thing I'm going to have to do is to get rid of this coefficient of 1,200. So I'm going to divide both sides by 1,200. So let me do that. 30,000 divided by 1,200 is equal to 25. So this means that my ending amount is essentially 25 times as big as my starting amount. But if I was talking about the context of accruing interest. Now I can either take natural log of this number with natural log of base this number on both sides, or I misspoke. I can take natural log of both sides, or I can take log of that base, 1 plus 0.04 over 12, as my base on both sides. Okay. I'll do the natural log version of this. If you wanted to take log base 1 plus 0.04 over 12, that's fine too. So I have natural log of this number raised to the 12x power. So I have to bring 12x out front of the natural log of 1 plus 0.04 over 12. When you solve this, you have to understand that 12x times natural log of this number. This is a numerical value. This is also just a numerical value. It's an ugly numerical value, ugly irrational numerical value, but it's still a number, right? So what we really need to do is we need to divide both sides by 12 and also divide both sides by that natural log number. Does that make sense? A lot of times I'll do this in steps when I type it in on my calculator. I'll show you how I do that in a second. So we're going to have to divide by the 12 and divide by the natural log. No. And so we get an answer that is x is equal to natural log of 25 divided by 12 times natural log 1 plus 0.04 over 12. Does that make sense? Hold that up in just a second. Like I said, when I do that on my calculator, a lot of times I'll do natural log of 25 and divide it by the 12 first, and then hit enter. And then divide that whole thing by the natural log of 1 plus 0.04 over 12. Does that make sense? Because you need to have both of those in the denominator. Okay. If you did it all in one line, you'd have to do natural log of 12, then you'd have natural log of 25, then you'd have to have 12 times the natural log of that whole thing, all in parentheses, so that you know both of those pieces are in the denominator. Okay. So we get approximately 80.61 as our answer. Just be careful about typing it in. I tend to do this where I divide by 12 first, and then I divide by the natural log. That seems to work well for most people. Okay. That's it. Now, this is as difficult as the exponential equation stuff gets. All right, that's about as difficult as the exponential equation stuff gets. That's a tough one. So we've done exponential equations with variables in the exponents. Now let's deal with some logarithmic equations. Okay. If I just have a log, and I don't have like log base 3 is equal to log base 3, then what I want to do is I want to isolate a single log on one side of the equation, single logarithm on one side of the equation. And then you can think of it as either rewriting it in exponential form or applying the exponent on both sides. Okay. I'll talk about what I mean by that more specifically in a second. So use the exponent on both sides or rewrite as an exponential form. Okay. When we're talking about rewriting as an exponential form, we're going to be remembering something like log base b of x is equal to c means b raised to the power c is equal to x, or x is equal to b raised to the power c. Okay, that's the rewrite version. We've seen this before. You don't have, again, that one's the same idea as our rules before. And then if we're talking about raising things to a power, then we're raising things to a power. So let me give you an example, or let me give you a couple of examples of what I mean by that. So we have log base 3 of 2x minus 7 is equal to 5. And then we have 5 times the natural log of x minus 14 is equal to 13. In some ways, these are like easier to solve than the exponential because these don't take any special change of base rule or when you have different bases with your exponents. Pretty straightforward. So here's what we're going to do. When I say apply exponents to both sides, what I mean is we have the log base 3 here. So I can think of taking 3 and raising it to this power. And setting that equal to 3 and raising that to the 5th power. You guys see what I'm doing here? I'm doing that rule we said at the very beginning of this section in reverse. So at the very beginning, we said if we had 3 raised to a power equaling 3 raised to the power, then the powers have to be equal. Now I'm saying if we have 2 numbers being equal, I can take 3 and raise it to each power. If I do that, then the 3 and the logarithm base 3 are going to cancel each other out, and I'll just be left with 2x minus 7 is equal to 3 raised to the 5th power. So that's one way to think of it. One way to think of it is like that. The other way to think of it is that if I convert this log expression into an exponential expression, it's just that exponential expression. This is telling me that my argument is 3 raised to the 5th power. So that's just a rewrite of your logarithm into the exponential expression. Do you understand what I'm saying there? So either way you think of it is perfectly fine with me. Usually I just skip this step and go into the rewrite, to be honest with you. Usually I do that. So that being said, this is just a linear equation that we can solve. 3 raised to the 5th power is 243. Then I would add 7 to both sides. Giving me 2x is equal to 250. Dividing both sides by 2 gives me x is equal to 125. That makes sense? So isolate the logarithm, and then you can either think of it as taking 3 raised to both of those powers, set equal to each other, or you can think of rewriting this logarithmic expression into the exponential equivalent. Now, the same thing would be true in an equation like this, although we have to isolate the natural log before we move on. Okay. So I would have to add 14 to both sides, giving me 5 times the natural log of x is equal to 27. Then I want to get rid of that coefficient of the natural log. So divide both sides by 5. And now I have natural log of x is equal to 27 over 5. You can write that as a decimal if you'd like. I think that's 5.4. It's nice when our decimals stop. Do that. And then you can think of taking both sides to the e power, if you'd like. Or not both sides to the e power. Reverse that. E to the power of both sides. Think of it that way, if you'd like. Or you can just think of this as rewriting what this expression means in exponential form. This means that x has to be e raised to the 5.4 power. That makes sense. E raised to the 5.4 power as your x. So that's 221.41 rounded up a couple of decimal places. That all make sense? Again, a lot of times I just think of it as taking both sides as powers of e. So this is one way to solve these logarithmic equations. Now, obviously, our logarithmic equations can get more involved. We have log base 3 of x minus log base 3 of 5. Set it equal to 2. And then we have natural log of x squared. Set it equal to 6. It turns out in both cases, there's multiple right ways of doing each. Multiple correct ways of doing these. So I'll show you a couple of different ways to do this one. And I'll show you a couple of different ways to do the other one as well. All right. I'm just gonna ask for suggestions. What would you suggest to do with this first one? The log base 3 of x minus log base 3 of 5 equals 2. Go for it, yeah.
Simplify and make it log 3 x minus 5.
Exactly. That's great. That's what I would probably do as well. Log base 3 of x over 5 using our quotient rule. Right? That's what we did earlier today. We took something with log with the same base subtracted, used the quotient rule, and rewrote it as one single log. That's what I would probably do. And then you can think of either taking 3 to the powers of both sides, or rewriting this as an exponent equation. X over 5 would be 3 raised to the second power, or 3 squared, however you like to say that. So whether you like to think of it as taking 3 as your base, raised to both of these exponents, or whether you think of it as rewriting, either way is fine with me. So x is simply going to be multiply both sides by 5, 3 squared times 5 is 9 times 5, which is 45. So x would be 45. That's probably the option that I would go with as well. That's probably your easiest option. I do want to point out that this log base 3 of 5 is just a real number. Right? It's an ugly, irrational real number, but it's a real number. So if I wanted to, I could add that real number to both sides. And end up with log base 3 of x on the left is equal to this messy looking number on the right. 2 plus log base 3 of 5. And then in the same vein as what we did over here, we can either think of taking each side, making that the power of 3, or rewriting this as an exponential equation, which gives me x is equal to 3 to this messy looking power. Is that okay? You can either do this by hand or you can just plug it into your calculator, either way. But if you plug it into your calculator, or if you do it by hand, you'll get 45. Sometimes it's hard for people to plug that into the calculator. Sometimes it's not. But you get 45 that way too. Okay. By the way, why would this is an irrational number. We're taking 3, raising to an irrational number power. We're getting a nice whole number. You know why that is? Rules of exponents say that this is three and log base 3 cancel each other out. I think so. We see that. So rules of exponents would say that has to go 45. Exponents and logarithms. So that's what's happening. That's why you're getting a nice whole number with this really ugly looking exponent. Make sense? Good. Let's go to this next one. Once again, this one's a little bit more intricate than that last one. I'll show you why here in a second. I'll do this two ways and show you that you kind of, some way get a different answer, some way not get a different answer. Depends on how it goes. All right, this one. Let's apply our power rule to this. So let's pull the two out front. And say 2 times the natural log of x is equal to 6. And then divide both sides by 2. That will give me natural log of x is equal to 3. And then again, think of taking e to the natural log of x on the left, e to the third power on the right, or rewriting as an exponential equation. Whichever way you like. That's x is equal to e to the third. Over here, what if I just did that immediately? What if I took e to the 6th power on the right and e to the power natural log of x squared on the left? I would get x squared is equal to e to the 6th. So x would be either the positive or the negative square root of e to the 6th power. So here, I'm getting either the positive or the negative version of e to the 3rd. When you take a square root of an even power, you get half of that power. So essentially, I get 2 answers here, a positive or a negative e to the 3rd. And I only got the one answer here, just e to the 3rd. The reason that I only got one answer here is because of the nature of this power rule. Okay. If you go back and look at the power rule, when we say log base b of m to some power is equal to the power times log base b of m, we assumed that m was positive because otherwise this would not exist. Okay, you can't take log of a negative number. So that would be undefined. So if I'm using the power rule, I'm only going to get the positive version of the answer. Here, I got both the positive and negative version of that answer. And if you're doing this on Moodle, just check that to see if they're asking for both the positive and negative or just the positive. A lot of times they'll just ask for positive, and you just give the one answer. Other times they might want both the positive and negative versions of that answer. That makes sense? So our power rule assumes that this x value is positive, otherwise it wouldn't make any sense. That's only something we need to worry about on even powers of x. Because if it was an odd power, then I wouldn't have this plus minus business to worry about. So there you go. That's all I wanted to point out. A little bit of an intricacy in that scenario. All right. Everybody feel okay about solving exponential equations and logarithmic equations? Pretty straightforward. Well, if you feel good about solving those equations, then the last section in chapter 4 that we're going to cover is going to be right up your alley. Basically, solving exponential equations, logarithmic equations, but in the context of applications. So it's applications of exponential functions. So we're just going to use an exponential equation in a word problem, or a logarithmic equation in a word problem. That's all. Okay. We've already seen a couple of the formulas that we're going to see again, so I'll just remind you of them. If you have a growth rate of R compounded m times per year for t years, and you input P as your principal, then the amount you'll have will be P times the quantity 1 plus R over M, all raised to the mt power. Okay. By the way, when you go to take your tests this week, make sure you have that equation written somewhere, right? It's a big one. You use that a lot. Also, have this one. This one is compounding continually. So if we are compounding continually at a rate of R, then it's A equals P times E raised to the R times T power. We've seen those first two in action. Now let me give you another example of an exponential formula. This is known as the doubling formula. Doubling means multiplying by 2, right? So if you start with some amount and you want to double it, then you want to multiply it by 2 over and over and over again. Okay. And if it doubles each 4 years, so if it doubles every 4 years, then we want it to be so that when we input a time of 4, then we get a multiplication by 2. Does that make sense? Therefore, we're just going to divide by D. D is called the doubling time in our exponent. So our exponent is going to be T divided by D. D there is the doubling time. That way, every time T reaches D, we multiply by 2. So it's P times 2 raised to the T over D power. Halving time is the same formula, but just with a half instead of a 2. And by the way, if I use a tripling time, I just put a 3 in there instead of a 2. And if I knew the quadrupling time, I could put a 4 in there instead of a 2. Okay. Usually we don't use tripling time or quadrupling time. Doubling time is much, much more common to talk about. So if an amount gets cut in half every time period of size D, then the equation is P times a half raised to the T over D power. Sometimes people put H for this for half time, halving time, instead of the D that I put. Doesn't matter which one you use. So let's do an example. The average half-life of glyphosate in soil is 47 days. Create an equation for the amount in the soil if you start with 450 milligrams in a cubic foot of soil using T for the number of days. And then how long until 50 milligrams of the glyphosate is in the soil? Everybody understand what's going on here? So glyphosate is chemical you put on, it's Roundup basically, but it's the active ingredient Roundup. We have 450, and then in 47 days, it's going to get cut in half. Every 47 days, it's cut in half. So you wait 47 days, on average, gets cut in half. Wait another 47 days, another cut in half. Another 47 days, another cut in half. Okay. So if we're cutting this in half, then we want to use the equation A equals P times 1/2 time over, again, I put D in there. Sometimes people would put H for half. Halving time instead of doubling time. So if you'd rather put an H in there, that makes more sense. For halving time instead of doubling time. Now, everything is going to be in days. So my time is going to be in days. My half time is going to be in days. Okay. So my equation is going to look like the following. We're going to start with 450. That's my principal or starting amount. And I'm going to put 450 times 1/2 raised to the T divided by 47. That way, when the T hits 47, we multiply it by 1/2. When we add another 47, multiply by another 1/2. Add another 47 days, multiply by another 1/2. So this is what the equation is going to look like. Now my question asks, how long until 50 milligrams is left? So let's say, when is the amount 50? And now this is just solving an exponential equation, just like we've done for the last hour and a half. Okay. Make sense? So solve this exponential equation, divide both sides by 450. By the way, 50 over 450 is 1/9. And then you can do whichever option you like, apply natural log to both sides or apply log base 1/2 to both sides. Right, we want to get this exponent, so we're going to do log base 1/2 or natural log. I'll do natural log to both sides. Natural log of 1/9 is equal to natural log of 1/2 raised to the t over 47 power. The exponent of t divided by 47 would come out front. And we'd end up with this. And then what I would do is I would divide both sides by a natural log of 1/2. And then to get rid of the 47 in the denominator, I would multiply both sides by 47. I'm gonna do that in one step. So t is going to be 47 times the natural log of 1/9 divided by the natural log of 1/2. And that's something I can type into my calculator. I get a t of 149.99. So about, or I'm sorry, 148.99. Excuse me. 148.99. So about 149 days. So if you start with 450 milligrams in a cubic foot, then in about 150 days, you'll have 149 days, you'll have 50 milligrams in a cubic foot. We okay with that? Again, Moodle may ask you to round to 2 decimal places. They might be okay with 0.99 of a day. But they also may ask you to round to a whole number to get 149 days. Just watch out for that. Whatever version it asks for, rounded to 2 or rounded to a whole number, just give that. Okay. So this is what happens when you're given the specific time period in which it takes some amount to be cut in half. Right? If I'm given a time period where some amount will double, like in this example, it says a certain bacteria doubles in size every hour and a half, or 1.5 hours. Then it says create an equation for the amount of bacteria in a dish if you start with 1,000 bacteria in the dish, using t for the number of hours. So we double every 1.5 hours. And we're starting with 1,000. Very similar to our last example, except now we're doubling. So we have a time period for doubling. So we take 2 and raise it to the t over d, where d is the doubling time. And it takes the double. So we have 1,000 times 2 raised to the t divided by 1.5. That's the equation that we'll be using. By the way, since 1.5 is in hours, t is also in hours. Okay. And then we could ask follow-up questions, like how many bacteria are in the dish after 3 hours? And then how many are in the dish after 5 hours? And we could ask how long until we have so how long until there are 1 million bacteria? Does that make sense? I want to point out that the first two are asking me to plug in a number into t and calculate the a. The last one is asking me to calculate the t by plugging in numbers for a. So plug into a, calculate for t, plug in t, calculate for a. These first two are probably a little bit more straightforward. After 3 hours, by the way, 3 divided by 1.5 is just 2. So that's basically just 2 doubling periods. So if we take 1,000, double it, you get to 2,000. Double it again, you get to 4,000. Does that make sense? So when you plug that in, you would end up with 4,000 bacteria after 3 hours. You take 1,000, double it, then double it again. You can also just plug it into your calculator. After 5 hours, well, 5 is not divisible nicely by 1.5. So we would just end up plugging it into our calculator. (1,000 times 2 raised to the 5 over 1.5 power. That would give me 10,079.37, again, bacteria. That's the projection. You might have 1 or 2 different, but that's what the projection is going to be. Right with that? And then we can do the exact same thing we've been doing most of the class period. And that is, on this problem, you set 1,000,000 equals 1,000 times 2 raised to the t over 1.5 and solve that for t. Divide both sides by 1,000. And we get 1,000 is equal to 2 raised to that t over 1.5 power. Now that we have our exponential piece isolated, I can take natural log of both sides or log base 2 of both sides. Either way. I've been taking natural log of both sides for a lot. I've done that a few times. Let's take log base 2 instead this time. So I'll take log base 2 of 1,000 equals log base 2 of 2 to that power. That's log base 2 of 1,000 is equal to t divided by 1.5. Then I multiply both sides by 1.5. So I end up with 1.5 times log base 2 of 1,000 is equal to t. That's something I can type into my calculator. So I'll do that. I got a time of about 14.95. By the way, this is all in hours, so the t was in hours as well. And so you get about 14.95 hours. That's how long it would take for that initial 1,000 bacteria to transform into 1,000,000 bacteria. That makes sense? So these are the types of questions that are in this section. A lot of these types of questions. For next class period, we'll finish this up. There's actually not a whole lot beyond this to do. Okay, so we'll finish this up next class period. And it won't take the whole class period. It will take, maybe an hour out of that 2.25 hours. Maybe not even that to finish up. So if you do have any questions over the test, bring those on Thursday. All right. Well, then I will see you all.